Well, just before we start, let's have some blatant advertising. That's a bit too loud. At least the weather's got better. I'm sure all this cold weather is a result of global warming, but not to worry. The next lecture, which is in a month's time, pretty well, is called Life on Mars, and I hope it'll be interesting. And the reason is that 2010 could be really quite a significant year in our understanding of whether life once existed on Mars. Do you remember some years ago, the Americans said they'd found evidence of life in a meteorite called ALH 84001? Do you anyone remember that? And it was largely poo-hooed. Well, more recent work that's currently going on, and hopefully will be resolved in the next few months, looking at that meteorite, plus another one, I might say, that's been in the British Natural History Museum, may well absolutely prove whether life did once exist there. So hopefully I'll tell you all about that in a month's time. We don't have one in March because I actually give the Gresham Astronomy weekend in the Cotswolds, which is great fun. We have 25 places in total, and as of last week 21 were full. So there may be one or two places left where we do optical visual astronomy, and it's a lovely place to go and stay, and actually very dark. And the final lecture this year is going to be called The Afterglow of Creation, which is about the radiation left over from the Big Bang. It tells us what the universe was like near its origin. Very pleasingly, my colleagues at Jodrell Bank have built receivers that are currently flying and working superbly on a spacecraft called Planck. What I can actually tell you of the results, I'm not sure. I have seen some, but I'm sworn to secrecy. But I'll see what I can do. Anyway, it's working incredibly well. So that's this year. I've already got some nice plans for next year, and I'll mention one of those a little bit later on. So anyway, I think it's almost time for us to begin. You probably know I'm a radio astronomer. But in a way, we don't ever see anything. We make maps, but we don't see anything. And for that matter, neither do professional optical astronomers. It's all done with CCD arrays now. But I do really like seeing things through a telescope with my eyes. The thought that the photons being captured by my retina may have left somewhere 12, 50 million years ago, I think is rather exciting. And I actually bought myself quite a big telescope this summer to try and see something where the light left there about 2,500 million years ago. In fact, I've got to wait until the spring because it won't be visible until then, but that's my target for next year. And you see, you're looking back into time. I think it's actually rather wonderful. And in fact, it's observing with a telescope or just with your eyes that has sometimes given me some of the most almost emotional points in my life, where what you see almost burnishes itself on your retina and you never forget it. I mentioned one of those at the last lecture, when I was happily, or luckily, one of the first astronomers, amateur astronomers, to see the scars on Jupiter caused by Shoemaker-Levy Nunn. I shall never forget that. But another night happened about 10 years ago when I'd been at a conference at Cape Town, and at the end we went up into the Karoo, near a town called Sutherland, where they have the largest telescope in the southern hemisphere, at a height of just under 6,000 feet. And it was a totally moonless night. When we got there, it was still twilight, and some of the professional astronomers, waiting for it to be dark, let us use a 1 meter telescope to look at one of the objects I'm going to show you tonight. I'll tell you which one. And then we went out under this totally dark sky. And it was just overwhelming. There were so many stars visible that you could barely make out the constellations. And if any of you ever have a chance to go to the southern hemisphere and look up at the sky from a really dark location, please take it. I can't, unfortunately, take you all there to show you directly the things I'm going to talk about this afternoon, but I'm going to at least try and show you what some of them look like. Some beautiful pictures, but not just beautiful pictures. I'm going to try and tell you some nice stories about some of them. So I think we should begin. If we could have some of the lights down, because that won't really be visible. I don't mind you all going to sleep, rather. It's getting a bit better. A little bit more if you could. That's going up. That's worse. That's better, thank you. Right, this is a wonderful image. It's actually a photograph, but it's made in the form of a chart of the whole sky, like the ones they make of the Earth. And this is, of course, our Milky Way Galaxy, with the heart of that galaxy here towards the constellation of Sagittarius and Scorpius. Now, sadly, this part of the sky is either not visible at all to us from our northern latitudes, or it's so low above the horizon we barely see it. And it does include the centre of our galaxy and also some lovely regions along here, till we come, in fact, to Sirius and this part of the sky which we can see. So I want to talk about some things here. Also, these are the large and small magnetic clouds. We'll talk about those as well, and one or two more distant objects. So this is the bit we're going to look at. That again is a wonderful image of the nucleus, the centre of our galaxy. You can't see it very well visually because of all the dust in these dust lanes here. And that's called the cold sack. We'll come to that later on. The reason that's there is because at the moment our sun is converting hydrogen to helium. When that process completes, in about another 5,000 million years, it will start converting 3 helium nuclei, helium-4, into 1 carbon-12 nucleus. So carbon is the first element, new element that's created in stars. That's why there's a lot of it. And that, sadly, is what is causing these regions, not sadly, but it's there, we can't see very well visually. Just another lovely view. This is Comet McNaught, actually. That is the large magellanic cloud. That is the small magellanic cloud. The centre of the galaxy is about here. This is the region going through Carina. That's Alpha Centauri. This is Centaurus. This is Crux, is there, and we go into Carina. See that lovely nebula? We'll come back to that later on. Now, if you use longer wavelengths, you can begin to see through the dust. And there's a wonderful spacecraft called the Spitzer Space Telescope that's observing in the infrared. And it sees far deeper into our galaxy and shows some of these lovely regions here of star formation showing up as a pinky colour. But it's looking right towards the heart of the galaxy, just about there. And that's a close-up view, and this is looking right at the very centre of our Milky Way Galaxy. If you use even longer wavelengths, you can actually begin to see the galaxy as it might appear from a great distance. This is COBE that made its observations about 1992. And this is an image taken by COBE, which is the only image that exists that shows, in a way, how our galaxy would look from a distance. You could see this central bulge here, about 3,000 light years across, and then we have this flat disk. Obviously, we're in that flat disk looking in towards the centre. So we are a nice, flat, so-called spiral galaxy. Not that optical astronomers can tell that we live in a spiral galaxy. From this, we could assume we do, because this is what other spiral galaxies look like from a distance. If we use radio waves, we penetrate the dust perfectly. And this is the Parkes telescope in Australia, and this is obviously our Lovell telescope at Manchester. And together with some help from a telescope in Germany, we mapped the sky long wavelengths. And I know this colour chart is really rather odd, but it shows you objects here. That's the Large Magellanic Cloud. And a little dot right in the middle there called Sagittarius A, it's the name we give it to it, which is one of the brightest radio sources in the galaxy. And it corresponds to the very heart of our Milky Way Galaxy. Now, we believe that there is what is called a supermassive black hole. It's something like about 10 million solar masses, maybe a bit more than that. Now, it's not something we can see, and I don't want to say too much about black holes in this lecture, because it's going to be the first lecture next year. So I hope you'll come to that one to learn more. But just to say, how on earth do we know there's a black hole here or anywhere else? Well, just think about this. We know what the mass of our sun is. We can't go and weigh it. But it has a gravitational force on our Earth that would pull it in. But there's an opposing force, centripetal acceleration, which if I had a ball on string and I went like this, you'd feel that force effectively. And those two have to be equal and opposite for the Earth to stay in a circular orbit. And by doing some very simple sums and knowing something called the universal constant of gravitation, you can calculate the mass of the Sun. And if the Sun wasn't visible, it was a black hole. Now, we couldn't be here because there'd be no heat or light, but let's suppose we were. We could still work out where it was and what its mass was, even though we couldn't see it. So if you see objects moving very rapidly around something you can't see, you can roughly work out what the mass is. If the volume that it can be contained in is not that big, you can deduce it must be a black hole. So we do have a black hole at the heart of our galaxy. Again, this is just showing these dark dust lanes due to the carbon. This is Orion. We see Orion. That's Sirius. This is the part of the sky we never see. We now believe this is what our galaxy would look like if you could go up into space and look down upon it. We are here. This is a bar. It's about 27,000 light years long. In fact, about the same distance as we are from the centre. Basically old stars, which is why it looks sort of a yellowy colour, whereas the stars in the spiral arms tend to be younger, bluer stars. Their light sort of dominates. So we think pretty much that's what it looks like. They did produce, this is done by Spitzer, they did produce a map a year earlier, which I really didn't like at all, because it didn't agree with the maps that my colleagues and I have made in the radio. And obviously other people didn't agree either, so they came out with this, and this looks spot on. So I'm pleased about that. Anyway, there's the bar. There's a very bright ring of star formation. It's sort of around here, that part and that part, where a lot of stars are being born. And so we live out towards one side in what's called the Orion spur. There are two major arms. This is the one we don't tend to see, the Scutum Centaurus arm. We're going to be looking at this region shortly. This is the part of the sky that we do see in Perseus. We did a lovely project a few years ago now, using one of our radio telescopes. We had 50 schools across the UK, all measuring little bits of the Milky Way to map out the spiral arms. None of them could do it individually, but we had a big event in the Royal Institution where we put all the data together and showed them, not the whole sky, but in fact a map of that part of our Milky Way. So it all fits in rather nicely. Okay, let's have a look in a bit more detail. This is Sagittarius, and you see he's a sort of an archer. I'm not very into that sort of thing really, but to be honest, all of us tend to think of Sagittarius as the teapot, because it does look like one. And there it is. If you imagine the water pouring out the spout, it sort of comes down, and there's a rather lovely cluster here, which is actually in the next door constellation, so we'll come to that in a minute. But there's some beautiful regions of nebulosity, particularly here, the Lagoon Nebula. And with binoculars, you don't actually have to go to the southern hemisphere to see this, but I remember sitting on the seashore on the coast of the Adriatic near Venice, looking south, and you could see this region beautifully with binoculars. That's showing you an image of it. There's obviously the teapot. It's nice how they draw these lines on the sky. And here you see the lagoon and the Trifid Nebula. And over here is another one called the Swan Nebula that I'm going to show you. But there are lots of clusters as well. Too many really to show you them all. That is the Trifid Nebula. You can see it's sort of a triform thing. And this is the Lagoon Nebula. And we'll close in again. That's a rather lovely picture. See these very dark clouds. That's the sort of region where there's a lot of dust, where it's quite cool, where stars actually form. And we only get these lovely pinky red colours where there are young stars, because I've said many times before that it is the ultraviolet light from these very young stars that excites the hydrogen gas and makes it glow. Rather like the way that the sodium streetlights are excited, and they glow in the orange colour of sodium. Well, one of the colours of hydrogen is this lovely pinky red colour. It's called H-alpha. And in fact, this one is lit up largely by the light from some very, very hot stars just there, and you can see that again, some very, very hot stars right in the centre there. This is closing in on the Trifid Nebula, and there are the bright stars that actually illuminate it in some sense. Very like, in fact, we have a group of stars called the Trapezium that illuminates the Orion Nebula. Just notice this little sort of unicorn type thingy. Isn't there some underwater animal that looks like that. Well, just look at that, and here is what the Hubble shows you. Isn't that wonderful? And you see all these little dust clouds shooting out. It's probably because tucked away in here somewhere is a young star. As stars come towards their period where they're stable, they blow off a lot of material, and there are outflows that tend to blow the dust around and give rise to these lovely columns like that. And that's another one, little one there. There's probably something hiding just inside there. The Hubble telescope has been a wonderful instrument, and I think one of next year's lectures might be the heritage of Hubble, the man himself and the telescope that's named after him. And here's the Lagoon Nebula, and that's actually visible to the unaided eye. You can see there's a little bright splodge of light, but looks quite nice in binoculars, even better, of course, in a small telescope. And you can see the clusters of stars that are being born at its heart. And here we have these dark dust clouds, regions where stars will be born in the future. A rather nice one. I've only really seen it once, and that was when I was staying with a friend on a visit to Hawaii. It's bad, all these name dropping, but astronomers manage to get around the world a bit. It's perhaps the best bit about being an astronomer. And we'd been up on the top of Mauna Kea, had some lovely viewing halfway down where there is an observatory for people to go and look at the sky at 9,000 feet. But we came down to my friend's house and we got his 10-inch telescope out and had a lovely look at the Swan Nebula. It also looks a bit like the Omega shape, so it's sometimes called the Omega Nebula. Very, very pretty indeed. So we'll move along the Milky Way to Scorpius. And it's obviously the scorpion with this nice tail. Actually, it looks a little bit like it. Now, sadly, this bit we see, Antares, it's a lovely bright red star. If you go to France, you can see that reasonably well, perhaps from southern Devon, you know, with a good clear southern horizon. But for us I live in Manchester, or near Manchester, not so good. Has this lovely tail around here. And I'm going to show you 4 things in Scorpius. There are 2 lovely clusters here, right on the boundary with Sagittarius, M7 and M6. There's a beautiful region down there, which, although that's its real name, we call it the southern jewel box. I think that's right, we'll come in a minute. And then there's a rather nice object here. So let's have a look at those. This is M6, and it's a beautiful open cluster. Now, it turns out that you cannot make a single star by itself. You can take a cloud of dust and gas, and gravity will try and make it collapse. But if you compress a gas, it gets hotter, and that will make it expand. And it turns out, unless you have something like 100 solar masses or more, you can't get a contraction to form stars. Turbulence will then break up the big mass of gas to give you lots of individual stars. So stars are born in clusters, typically several hundred at a time. And that's a very lovely one here that we see in Scorpius. The second one, not quite as pretty, but you can see the wonderful background of stars that makes up the Milky Way, is called M7. The M, as I'm sure many of you know, is after Charles Messier, who made this wonderful catalogue of interesting objects in the sky quite some time ago now. There are about 110 of them, and the ones he could see from Paris all have the letter M. Things further south he obviously couldn't see. There is a new catalogue, in fact made by Patrick Moore, which includes some of the more southerly objects. His name is M, and he obviously couldn't call it M, because M's already taken, so he used Caldwell, which is his middle name, and so it's the Caldwell catalogue. And this is the northern jewel box, because it can be seen from the north. In a telescope, it looks a bit like a comet. Can you see the sort of bright nucleus here, which is the cluster, but you get this sort of streak here, and the eye can't normally see the red. It just sees this as fairly bright. So it looks like a comet with a curved tail. And that's a rather beautiful object, which is very, very nice in binoculars or a small telescope. You don't need a big telescope to see objects like this. The bigger the telescope, the less sky it sees at one time. And that's a close-up of the northern jewel. Doesn't it look lovely? These are red giant type stars. They're stars that have aged. They've come to the end of their so-called main sequence life. They've burnt up their hydrogen to helium. They're now, in fact, producing things like carbon, oxygen, maybe up to silicon. And they expand, they get much bigger, and they get cooler, at least the outside, and that's why they go reddish. And this is called a globular cluster. It's one of the nicest ones in the sky, M80, it's obviously in the Messier catalogue. Globular clusters are spherical distributions of stars, as you can see there, maybe 1 million or so stars in each globular cluster. They date from the origin of our galaxy, which is about 12,000 million years ago. So they're sort of remnants of the formation of our own galaxy. You might call them microgalaxies in a way, and they're orbiting our galaxy in a sort of a spherical distribution. If this is the flat plane of the Milky Way, they form this spherical distribution. We're going to come to another one of those a little bit later on. That's M80. Well, the next constellation is a very big one. It's called Centaurus. And it actually, rather nicely, or interesting, it sort of wraps around the smallest constellation in the southern sky, which is called Crux. We normally call it the Southern Cross. There are two very bright stars, Centaurus Alpha and Beta, or Alpha Centauri, Beta Centauri here. And they're often called the pointers because they sort of point towards the Southern Cross. So we'll have a look at those. Here is a rather lovely picture of that part of the sky. That's Alpha Centauri, Beta Centauri. That's the Southern Cross there. This is the thing called the coal sack. And there are other interesting parts, objects in Centaurus as well. Notably, not that it'll be obvious to you, that object there. So we're going to have a look at some of these things. That's a beautiful image, I think, showing Alpha Beta Centauri. The coal sack Crux we come to, and I don't think that looks particularly different from a star. It isn't a star, and we're going to come to that shortly. So what about the two stars Alpha and Beta Centauri? Alpha Centauri is very bright, and that's essentially because it's very close. It was thought originally, I think, to be one star. We now know it's a combination of two stars, roughly the same size as our Sun, that are going round each other, I think, about every 5 days or so. And they are about 4.4 light years away. And this is just a comparison of them relative to our Sun. So Alpha Centauri A is a bit bigger and brighter. Alpha Centauri B is a little bit smaller, a little bit less bright. So together, they give us the effect of that bright star. Now, there's another star, a very faint red dwarf star called Alpha Centauri C, which we believe is orbiting the other two. Can't guarantee that, but it's thought to be. They're all moving in the same sort of direction. This one is not normally called Alpha Centauri C, it's called Proxima Centauri. And that's because it's the nearest star to our Sun. 4.2 light years away. So that's the closest star we have. A little faint red dwarf. It's 11th magnitude. It means you can see it, perhaps not with binoculars, but with a not too big a telescope, a 6-inch telescope, you could actually see it. The other thing I want to show you here, those are the pointers. If you go from that star and sort of turn left and look up here, the same distance, you come to that object called Omega Centauri. And it is there, and it's just perhaps beginning not to look like a star, although this photographer has used a technique where he's made the brighter stars become somewhat blurred. It actually helps show you the colours better and also makes them stand out. It's done, well, some of you into photography, you'll know about these soft focus filters that are used for portraiture. I won't say why. You can buy them, they're quite expensive. You get just the same effect by actually stretching a pair of black nylon stockings over the front of your telescope. I got some bad looks when I bought mine, but anyway, it does make a rather nice effect. But it does actually, these would be starlight, but that would still remain fuzzy, even if you didn't use one. And that's what it looks like in a photograph. It's about the size of the full moon, so it's actually quite big. And it's called Omega Centauri, and there's a wonderful image of it. It's obviously a spherical cluster of stars, and until quite recently it's been thought to have been a globular cluster, and the biggest and brightest globular cluster in our heavens. However, as people have analysed the star types that are found within it, and here is a Spitzer, remember that infrared spacecraft, a Spitzer image, showing lots of these red giants. Whereas all the stars in a globular cluster, they all sort of date back from 12,000 million years ago, here there are lots of different generations of stars. And for that reason, I think we now believe it's not a globular cluster, but the core of a galaxy whose outer parts have been stripped off by the gravitational effects of our own Milky Way. And there's one thing that sort of confirms that, because right at the heart here, it looks as though there's one of these black holes. Not a very massive one, it's about 40,000 times more massive than our Sun. That's an intermediate-sized black hole, the first one I think that we know exists. Again done by plotting the motion of the stars near the centre. So probably it's not a globular cluster. One interesting point, the Hubble Space Telescope has looked here and studied 34,000 stars to see if any of them show a light curve that drops, goes along and comes up again, which would indicate the presence of a planet in orbit around it. This is one way that we're detecting so-called exoplanets. Well, they found none. So it implies that in this, whatever the object is, planets have not formed in the same way that they have in our own Milky Way galaxy, where I think we think there are 6 billion giant planets orbiting stars in our galaxy. In here, they found none. Well, I've mentioned Crux a couple of times, the smallest but a rather pretty constellation, because we all have heard of the Southern Cross. There is the cross here. There are two other things in the constellation, as we shall see. And that's the Southern Cross here. There's Alpha and Beta Centauri, pointing towards it roughly. There's the coal sack. I've just sort of put some names on there just to help, not really needed. And this is how they look. A photograph taken from Uluru. This is it was Ayers Rock, wasn't it, originally, but then it's Uluru now. And here you see Alpha Centauri, Beta Centauri, pointing to the Southern Cross, which is there. It's not a brilliant photograph, but it just shows them in the sky. Now, some stars look brighter than others. That can either be because they are very bright but a long way away, or they could be quite faint and nearby. So when you look at the sky like this, you don't necessarily know which are really fundamentally bright stars or not. If you can work out their distances, then in fact you can get a real idea of what's going on. Just notice that Beta Centauri doesn't look nearly as bright as Alpha Centauri. Well, there's a lovely picture showing the cross. Again, they've done this little fuzzy trick to make the brighter stars show up. These, as we shall see, these four stars, I think, are all relatively close together. One of them is further away. And this is the way we can measure the distances of relatively nearby stars. Here's the Sun, here's the Earth going around the Sun. If we make an observation of a nearby star in April, we might see it against a certain background of stars. If we wait 6 months till October, it will have apparently moved against the distant stars. This is, of course, incredibly accentuated. But it gives you the idea. If we know what this angle is, it's called the parallax angle, we know that distance, 1 astronomical unit. One of the very first good values of that was done by radar using our Lovell telescope at Jodrell Bank. Then we can find the distances. So that's been done for those stars. And here's Alpha Centauri. Remember I said it was one of the closest? Well, they've said here 4.39. Well, I would have said 4.41, but who cares? A little bit. But notice Beta Centauri is about 500 light years away. Can you see? That's 5, say. That's 500. That's a factor of 100. Now, if they were both the same brightness, fundamentally, this star would be 100 squared, 10,000 times less bright than that one. Do you see that? The fact it only looks about half as bright means it must be probably 5,000 times brighter than Alpha Centauri. its actual luminosity is very great. It's actually one of the brightest stars that we can see. Well, here we have Crux, and you can see some of these are really very close. We think they're actually all part of what's called an association. As clusters age, the stars spread out. And we were once in a cluster, but you can't immediately say which stars were related to our own Milky Way. The stars you see in the plough, they're all related. They're all born at the same time. So we think that these are all the same. One of them, however, let's get this right, this one, Gamma, is actually much closer, probably not part of them. So this is how we can measure the distances. Once we've got the distances of stars, then we can actually say how bright they really are. Well, there's a very lovely object in Crux. It's called the Jewel Box. It's just below here. And did I say what it's called? Yes, Sir John Herschel. He was the son of William Herschel, very famous astronomer in his own right. And he basically made some of the first surveys of the southern sky. And he called it a gorgeous piece of fancy jewellery. And that's a large-scale or small-scale image, shall we say. And that's a large one. What makes it look really nice is that these are largely blue stars. They're young, bright stars. And that's one that's aged. It's become a so-called red giant. And there's a little cluster called M41 south of Sirius, which it looks very similar. And you get a lovely colour contrast. And then I've already mentioned the coal sack. This is perhaps the darkest region in the Milky Way. A great cloud of carbon dust and silicon as well that's blocking the light from behind. Another nice view of it there. Well, next along from Crux, there was a constellation that was originally called Argo Nabis. And you see it's a ship. I do love the face on the ship here. Now, that's been split up, effectively into two constellations. The upper part is now called Velar, from the sails. And the lower part is called Carina, from the keel. Careening, isn't that that horrible thing they used to do to people? Same word, I think. Isn't Latin great? I hated it at school. Anyway, here it is. And we've got Carina down here, Velar up here, and there's a rather nice cross here, which is called the false cross, because lots of sailors used to mix it up with the real Southern Cross and use it for navigation, and hence go a bit wrong. So you need to know that the one that's obviously bright cross is not the real one. The Southern Cross is a bit fainter. And there's a rather lovely planetary nebula in Velar. It's called the Burst Nebula. That is the remnant of the star that exploded. It's called a white dwarf. Our sun will look like that eventually. The outer parts of the star get blown off. The colours you see, the reddish colours, are essentially hydrogen, but the greeny blue in here is in fact oxygen. It just proves that our stars are generating, they're sort of creators, they're doing alchemy, they're making other elements. And the other thing of note in Velar is the so-called Velar supernova remnant. This is the remnant of a star that actually exploded, we think, about 11,000 years ago. And that's the remnant gradually expanding out into space, these little wisps that you see. Now, the interesting thing is that the remnant is still there, the bit that was left behind. It actually proved that something was left behind when stars explode. This was the first one that was related. We call these things neutron stars. What's left in the core collapses down until it's about the size 20 kilometers across. Gravity is so strong, it fuses the electrons and the protons into one. So the charge cancels out and they become neutrons. So the whole of this object is basically made up of neutrons. It's incredibly dense. 600 million tons per cubic centimetre, denser than a normal nucleus of an atom on Earth. And obviously it's very heavy. The star that blew up was probably 10 or 12 solar masses. The bit that's left behind, typically 1.3, 1.4 solar masses. So you've got the mass of our sun, more than, collapsed down into a volume the size of a city. Now, stars are rotating. Our own sun rotates once every 25 or so days, depends quite where you look. And when the star, the bit in the middle, collapses down, conservation of angular momentum means it spins up. So initially these objects might be spinning 20, 30, 40 times a second. they have an enormously powerful magnetic field. And that's usually, as in the case of the Earth, not aligned with the rotation axis. As this spins around, you get beams of usually radio, but in this case and some other cases light, that sweep around the sky just like an interstellar lighthouse. I know I've talked about these before. If that was the rotation axis above me, then one beam would sweep around like that, one beam would sweep around like that. If we happen to be somewhere where that beam would cross in the sky, then as the beam points to us, we get a pulse of energy. Oh, I thought that was going to carry on going. Doesn't matter. Anyway, this goes round, you get this lovely little pulse of energy there. Now, because these are rotating very accurately, they're very good clocks, then we call these things pulsars because we get a very regular series of pulses. And this particular one can be seen pulsing in gamma rays. It's actually slowed down by quite an amount. It's spinning around 11 times a second. And it is, in fact, the brightest continuous source of gamma rays in the sky. And it's actually here, and there are little shock waves that are going out from it, and a bit of a jet as well. It's a very dynamic object. As I said, it's spinning around 11 times a second. If we take the signals that our telescopes receive, these little regular radio pulses, we amplify them and apply them to a loudspeaker cone. The loudspeaker cone gives you clicks. And all being well, this is what it sounds like. It's rather nice, isn't it? Well, we'll come to some more of those in a minute. So that is, in fact, the Velar pulsar, a neutron star spinning but giving out this beam of light and radio waves that sweep around the sky 11 times a second. If, in fact, we ever got to the point of navigating through our galaxy, these objects would be used, you know, as navigational beacons, just like lighthouses. In fact, some of you may remember that the spacecraft that have left our solar system, 2 Voyagers and 2 Pioneers, Pioneer 10 and 11 I think, they all carried plaques, and on them was a chart that showed the position of our Sun relative to, I think, 16 of these pulsars. So anybody that ever found it, which is highly unlikely, but if they did, they could actually work backwards to find out which star the spacecraft had come from. Just in the way that if we take bearings on the number of lighthouses in the channel, we can work out our location. It's all done by GPS now, but that's how you used to do it. Anyway, that's rather nice. And the interesting thing too is that pulsars slow down with time. So that when they got this, some millions of years in the future, those pulsars wouldn't perhaps be spinning at the same rate, but they could actually work out backwards when it was the spacecraft left our Earth. That's rather lovely. Okay, now, we'll come now to, down here, this region called Carina, and it contains the second brightest star in the sky, Canopus. And this is an image that actually shows Canopus and Sirius. And you can see Canopus isn't quite as bright, but nevertheless it is a very, very bright star. So let's just do a little bit about stars. 2 guys, Hertzsprung and Russell, both independently plotted on a graph the luminosity of stars, and here our Sun, which is there, is 1. So this is 100 times brighter than the Sun, 10,000, a million, and that's getting fainter. Against the spectral class or colour or temperature, it's all related. These are cool stars relatively, these are very hot. Perhaps 20,000 degrees surface temperature, about 6 for our Sun, down here more like 2.5 to 3. You find on a plot like this that most of the stars lie on a bit of a curve like this. It's called the main sequence. It's where stars spend most of their time while they're burning hydrogen to helium. And this plot actually rather nicely shows that there are many, many more faint stars than there are bright stars. When stars stop burning hydrogen to helium, they start going beyond that to form the carbon, the oxygen, and so on. They become giants or even supergiants. They get larger and cooler, so they become redder, but they get brighter, so they're up here. And this is a blue supergiant as well. And you see the brightest stars can be 1 million times brighter than our sun, and that's pretty bright. When these things finally blow up, as you saw that little planetary nebula, what's left behind is called a white dwarf, the little star in the middle of that sort of egg-shaped thing. This is being slightly more specific, but there is our sun on the main sequence. Here is Sirius. So Sirius is brighter than our sun. It's also quite close, which is why it looks so bright in the sky. Now Canopus, which isn't as bright as Sirius, the second brightest, is up here. It's about 13,500 times brighter than our sun. So that's a pretty bright star. There aren't many like that. In fact, it's one of the brightest stars you can actually see with your unaided eye. And here's just a thought. Our sun is going to live in total for about 10,000 million years. We're about halfway through, so don't need to worry. Canopus, as I've just said, is 13,600 times more luminous. But that means it's burning up its fuel about that times more quickly. However, its mass is only 8.5 times the mass of our sun. So can you see it can't live very long? And you can do a rough calculation. If you take 10,000 million years, you multiply by the fact there's more mass, but you divide by the fact it's burning up more quickly, and you get somewhere about 7 million years, not 10,000 million years. These very hot stars have a very short, very bright and active life, but they don't live very long. There's also a very lovely region, or a little cluster called the Southern Pleiades. I'll mention that again later on. So it's a sort of a southerly version of our Pleiades cluster. Looks rather sweet. And then we have in Carina, the Carina Nebula. This is a wonderful thing. It doesn't look dramatic, doesn't it? With all these are all things caused by stars blowing off material and forming these lovely knots. And that's a little thing called a proplid, and that one there. They are places where stars are actually beginning to form. That name was coined by one of my colleagues at Manchester, actually, as seen in our Orion Nebula. Now, in that overall nebula, there's a region around here with a very bright object there, and that really is rather special. This is that small part, and this is what looks like a very bright star. Well, it is a star, but it's a bit more dramatic than that. It looks like this. Now, that's not a very large magnification, but let's zoom in a bit. Now, this star is called ItaCarina, and it was, for a time, about 150 years ago, the second brightest star in the sky. But then, it had a major outburst. A lot of the outer parts of the star were blown off, and they caused this outflowing two sort of lobes of material. And when they weren't very far from the star, they basically just stopped you seeing the star at all. So the star virtually disappeared. But gradually, over the last 100 years, as the lobes have got bigger, they've become slightly more transparent, and you can begin to see the star again. And a few years ago, it doubled in brightness, so you can just see it with your unaided eye now. So this star has undergone a very major event. And in fact, not many stars would survive it. It is still there, but it's surrounded by this outflow of dust. Now, something to note, do you see there's a line, an axis here, which encouragingly is not pointing at us? That's the important thing. Now, that's just a Hubble image showing the star in here, and the axis, to say we're here, is pointing a bit over that way. Why is that encouraging? Because this is the next object in the sky, the next star, that we think is going to explode. And it's such a massive star, it might not just be a supernova, it might well become a hypernova. And when a hypernova explodes, it gives rise to a black hole, and you get an enormous burst of gamma rays that are aligned along the axis of whatever it is rotating, which is the same axis as that axis there. So if you were down here, when it exploded, it would not be a nice place to be. And if that were pointing at the Earth when it exploded, the equivalent amount of energy of about a TNT, one ton of TNT, per square kilometre on the Earth's surface, in the form of gamma rays. I don't think it would affect humans on the ground, because the atmosphere will protect us. Any spacecraft or satellites in orbit would certainly get destroyed, as would, I think, the ozone layer. So it would be a major problem. Now, it looks as though it ain't going to be pointing at us. However, there's a thought it might be in a binary system. If it's in a binary system, the actual direction of that beam can precess over time. So keep your fingers crossed. But I think it's safe to go to the southern hemisphere. OK. Another globular cluster. It's very close to the small magellanic cloud. We'll come to that shortly. But this is a globular cluster, just like the ones I talked about. It is incredibly compact in the centre. Stars are very close together. And in there, we have discovered, right in the heart, quite a number, about 24 now, I think, of what are called millisecond pulsars. Pulsars that aren't spinning 11 times a second as the one I played to you, but a passing star has gone past, material has fallen on the object and spun it up, just like whipping a top. And some of these are spinning, in this particular object, 500 times a second. It means that at the equator, you will be travelling around at 15% the speed of light. That's quite something. Now, this, in fact, is an image right of the very heart. It's amongst here that these objects exist. We've actually got here the pulses of 16 of them, one after another. Now, of course, if you apply pulses to a loudspeaker cone that are faster than about 50, then you actually hear a tone. So you're hearing sounds, although, of course, it's radio waves that are coming across space. I like that one. That's the whole lot at once, a sort of a stellar cacophony. We might just play a little bit of this. This shows you what would happen if you sort of flew around inside. You'd hear different ones as they come nearby, above the background. Sorry, I'll move my mouse. That's as good as any modern music, isn't it? In fact, we've actually live recorded or picked up signals like that and sent them across to Huddersfield, where they have a modern music thing, and as part of the live performance. Okay, right, they're rather fun, aren't they? Now, the magellanic clouds. This is the large, this is the small. Let me just say one or two things about them briefly. They're members of what we call our local group of galaxies. There are about 50 galaxies. The Large Magnetic Cloud is the fourth largest. Andromeda, our nearest neighbour, is the biggest. We come number 2. There's a galaxy in Triangulum called M33 is number 3. This is number 4. And it's about a tenth the size of our own Milky Way galaxy, so it's quite big. It was thought they were orbiting our galaxy. But if they were, you can work out the mass of our galaxy from the fact they're going round at a certain speed, and it does make our galaxy a bit more massive than we think it should be. So we now tend to think they're actually just passing by. So we're seeing them nearby. This is the small. If they'll cut this out of the video, I'll say a slightly traumatic event when I saw these in southern New Zealand a few years ago. Has anyone been to Milford Sound? I suspect somebody has. On the way, you go through a place called Fjordland, and we stayed overnight at a not particularly good hotel called the Fjordland Hotel. My wife and I were quite lucky because instead of having a room in the hotel, we had one of 6 apartments sort of in a line outside with sliding French doors. They had cookers and things as well as beds. So that's where we were. About 1 o'clock, my wife woke up and said, "Oh, it's clear. Most of this trip we've been staying in cities, so that the night hasn't been very dark." So I put some clothes over my pyjamas, went out with my binoculars, got well away from the hotel, and had a lovely look at the Magellanic Clouds. I'd left the door of our sliding French doors open by 2 inches, so I'd know where I was. Anyway, I came back after about 3/4 of an hour and found the door 2 inches open, walked over, took my outer clothes off, was just about to climb into bed when there was a shriek from a lady, and "What on earth are you doing?" or words to that effect from a gentleman. And unfortunately, the people in the room next door had left their window open by just the same amount. We left very early the next morning and have no idea who they were. Anyway, so they are rather impressed upon my mind. That was 47 Tucani, but this is the smaller of the 2 Magellanic Clouds, named after Magellan, of course. It has a rather interesting story in the history of astronomy. A long time ago, John Goodricke, British, he discovered that a star called Delta Cepheus was basically changing its brightness in a very regular way. 5 days, 8 hours and 48 minutes. And essentially these are very, very bright stars, and they have a very regular periodicity in their brightness. I've shown you a Hertzsprung-Russell diagram. Here's our sun again, but look, these objects, these Cepheid variables as they're called, are right up the top. So they are probably 100,000 times brighter than our sun. And that means you can see them for a very long way away with a telescope. That's the important thing. Now, there was a lovely lady called Henrietta Swan Leavitt. She was born in 1868. Sadly, she died from cancer in 1921. She joined Harvard Observatory in 1895 as a computer. And her task was to analyze photographic plates and find so-called variable stars and measure the brightnesses of stars. And she became head of the stellar photometry department. In fact, she discovered 2,400 variable stars, half of those that were known at the time. Now, Harvard built an observatory in Peru. It actually went from Peru a long time ago because it wasn't a very good place to have it, and they took everything across to South Africa. So these images, I'm afraid, aren't very good. But that does in fact show you where the observatory was, where it was, in Peru. That's a 24-inch refracting, really a camera, just a wide field camera. And this was used to take lots of pictures of the small Magellanic Cloud. And in those images, Henrietta Leavitt discovered these Cepheid variables. Now, notice, if this is where we are, that's the small Magellanic Cloud. Can you see all the stars here are about the same distance? So if one star appears brighter, it really will be brighter. And so she noticed, this is a sort of rhythmic breathing, that the brightness of the Cepheid variables depended upon the period. The longer period ones were brighter than the short. You shouldn't be surprised about that. If you take a big bell, it rings with a low tone. A small bell rings with a higher tone. So a more massive Cepheid variable probably will vibrate, oscillate more slowly. And they're typically 10 to the 4th, 10,000 or so times brighter than our sun. Now, if you know how far the small Magellanic Cloud is, and you see a Cepheid variable there with a certain period, if you saw a Cepheid variable with the same period, perhaps 10,000 times fainter, in a distant galaxy, you'd know it was 100 times further away, the inverse square law. And that was how Edwin Hubble, using the 100-inch telescope on Mount Wilson, was able to make a first measurement of the Andromeda Galaxy. This is a very famous photographic image. That's the heart of the galaxy. This is a star he thought was an N-type star, but notice he crossed the N out and put variable. It was a Cepheid variable, and it showed him that M31 was way beyond our own Milky Way Galaxy. He later used the same technique to measure the distances of about 20 or 30, 24 galaxies. Combining that with other data from someone called Slipher, he came up with Hubbles Law. I've often thought it should be called the Slipher-Hubble Law. Perhaps because it was also based upon Henrietta Leavitt's work, it should be called the Leavitt-Slipher-Hubble Law. In fact, her work was probably worth the Nobel Prize, and there was in fact a move to give her a Nobel Prize in, I think, 1928. But sadly, when they actually contacted the observatory, they realized she'd just died of cancer, which is very sad. A wonderful lady astronomer. The Large Magellanic Cloud has this fantastic region of star formation. I looked at that with a 1-meter telescope in South Africa. It's brilliant. Look at it here. This is the biggest star formation region we know of in our local universe. It's called 30 Doradus, and there's a wonderful cluster here that makes it bright. Now, the great thing was that in 1987, a star became a supernova. This was the star here. It's obvious which it is because there's an arrow in the sky. And that one turned into that. And for a while it was bright enough to see with the unaided eye. It was discovered by Ian Shelton with his telescope. He was in Chile. He took a photograph. He actually developed it just after he took it, and there he saw this bright object. In fact, the night assistant saw it visually as well. So jointly they were the discoverers. Now, in fact, some hours earlier, an astronomer, Albert Jones, in Australia, had also photographed, and it was on there as well. But he went home to bed saying, I'll process the image in the morning. So in fact, it was Ian Shelton that's the discoverer. So we know pretty well when the light arrived. But interestingly, a burst of neutrinos was detected 3 hours earlier. Now, this is a wonderful piece of serendipity, because these things weren't built to detect supernovae. They were built to try and see whether protons decay. A physics theory in the late 70s said that if a proton, if you look at it, for 10 to the 31 years, there's a 50% chance it would no longer be a proton. This would be embarrassing. Now, you can't do that experiment because it's a bit tedious. But can you see you could take 10 to the 31 protons and half of them should go in 1 year, or some mix. So they built these big tanks to contain protons. Water, H2O, 2 protons in every molecule. And they're surrounded by these photodetectors to detect light that's caused if a proton decays. But it so happens these will detect neutrinos as well. And they detected a burst of 25, there were 3 of these, and they detected 25 neutrinos. In fact, you can actually tell the direction in which the neutrinos come from, and they did come from the right sort of place in the sky. That's the sort of event that we have here. And I said, 5 billion pass through each square centimetre of the Earth's surface. They arrived 3 hours before the light. That's because the neutrinos come from the core of the star as it collapses. The light doesn't come until a shock wave has travelled out through the star to reach the surface, and that took about 3 hours. So the neutrinos had a head start. Incidentally, can you think of a little volume containing protons which has got detectors around it, of which we all have 2? Our eyes. It is actually thought that perhaps 10 people in the world would have had a flash of light when those neutrinos passed through us. That wasn't me, sadly. What we think, I've got to be fairly quick now because we're running out of time. It was a very odd star. It's actually thought that 2 stars basically merged together some 2,000 years ago. And the primary star gobbled up the small one. A lot of material was thrown out at that time. An outflow of gas, and this torus of material. This is quite important. Then the primary star exploded as a supernova. Now it says here that caused the inner edge of the ring to glow. Yes, but only when the light, the ultraviolet light from here, reached there. And that took 235 days. So can you see, we know that distance. It's 235 light days. Here's the Hubble image. There and here. This is when that shell got lit up. But we know from Hubble that that's 0.86 arc seconds. So if you know that angle and you know the distance, you can work out how far away it is. And this has given us a very accurate measurement of the distance of a large magnetic cloud. That's actually quite important. So 232 days, I'm sorry. So we actually now know that that supernova is 168,000 light years away. That's quite important. Now, however, ejecta from that star continued to flow outwards, and eventually it started interacting with this disk of material and made it lighten up like that. Here is a sequence of Hubble images showing you what happened. It started off just as a red ring, but then it began to brighten up, just like a lovely jewel. You get the idea. Isn't that lovely? I said there were some lovely things in the Southern Hemisphere, and that's the later picture from the Hubble telescope, showing this wonderful ring lit up like a string of pearls, really. So finally, just a couple of minutes' time, there's one other lovely object in Centaurus, NGC 5128. It's the fourth brightest galaxy in the sky. We think it is the collision of an elliptical galaxy with a spiral galaxy, and it's caused a major disruption here. You see these enormous dust lanes. It's a fantastic region of star formation as well. And that's a VLT image. These are the wonderful telescopes in Chile I talked about last autumn. And that's the image from the VLT showing this central region, obviously very disrupted. Going even closer still is the Hubble Space Telescope image. We can't see a lot what's going in there with visible light, but you can with other instruments. In particular, there's a Chandra X-ray observatory, and it's observed this object. And after 7 days, it shows this wonderful X-ray jet. That's about 30,000 light years, the distance from our Earth to the centre of our Milky Way. So it's quite a big thing. So that's the jet coming from the centre. We believe, again, there's a supermassive black hole, about, I think, 10 million solar masses at the heart of that galaxy, and that is making this jet come out in this direction. Again, much more of that first lecture next year. Notice also lots of other little X-ray sources. These are all mini black holes, the remnants of stars that have exploded. And what can happen is that if that's the black hole here and there's a companion star, material can flow onto that, forming again these jets. In fact, I helped discover where one of these objects was in our own galaxy many years ago now, and we'll talk about that next year as well. So it's a very interesting place. So we see X-ray information, we have visible information about it, and also we can make radio maps of it. And there are these vast lobes of radio emission. It's a very bright radio source, which is why we call it Centaurus A. That's the brightest object in the radio in a particular constellation. And you can combine the images in X-rays, in radio, and in optical to make some wonderful images like that. And that's my final slide. But I just want to make the point that nowadays you're not a radio astronomer, you're not an optical astronomer. You basically use all of the instruments that are available to you. From the X-ray, now gamma rays as well, through light, ultraviolet, visible, infrared, and then radio. And it's by combining all that information from all those wavebands we learn about the things we're looking at. Thank you for listening.